My name is Jordan Hibben, and we are the wireless power transmission group. So, an update from the last time, which we showed some pretty bad simulations, are some more horrible simulations. So as you can see here, we tried experimenting with a different type of patch, kind of adjust with the sizing, match the feed lines this time, and this is the pattern that it outputted. So, it's not directed at all. It is going in the Z direction, but then again, it's going everywhere. So we ran another test with a antenna called the Vivaldi antenna, which is basically a modified slot antenna. And this was the initial design, and here's what the radiation pattern looked like, which is, again, just radiating business everywhere and not smooth at all. So we tried to modify the Vivaldi again, could do another iteration, and this is the radiation pattern of that second design. As you can see, we're starting to get some more, lobes going, but we have some sort of spill behind where we want it to radiate, which is not ideal. Here's what it looks like in HFSS, this time with substrate actually underneath where the copper would go around. Again, the radiation pattern from this design looks like this. I am now going to pass it on to Armand, who's going to talk about one of our great breakthroughs.
Yeah, so my name is Armand Villani, and as Jordan mentioned, I'm going to be talking about one of the breakthroughs that we had in designing our feed element. So one of the things we had before is we did take this kind of approach where you can see sort of a microstrip patch antenna that has kind of a slot cut into it, and the reason that you would do that is for impedance matching. But we'll see something was wrong with the simulation. We think it was either something wrong with the file or the way things were defined. We're really not sure. So we decided to just kind of start from scratch with it. As you can see, that's the pattern, as you may have seen before, that we got off of this design. So we started from scratch with it, and this without a feed line. That's that kind of microstrip feed to it. We get this kind of doubly lobed shape, which is really not good. What we're looking for is, you can see in the Z direction, we'd want one major lobe. So playing around with this a little more, we got to this step, and I said, okay, what does it look like when we have a microstrip feed leading up to it? And here you can see that we do get this one major lobe, and it is primarily in the Z direction. So we're happy with this. We think we get pretty good directivity. We can fabricate a parabola of reasonable size that will accommodate this feed. And just talking a little bit about why you notch things like that, like I said, it's for impedance matching. This one does lean a little bit forward. It's hard to see in this picture, but it does lean a little bit off the Z-axis. One of the reason for that is that an online calculator was used to get the width of this microstrip, and after examining the value that came out of that and going through a microwave textbook and looking at the kind of equation that's used to get these strips, we came out with a value of 1.94 millimeters for this strip line, whereas the online calculator gave us 1.9. So we think that potentially causes a little bit of a mismatch, that discrepancy, which may be tilting our beam. So we're going to look at fixing that and actually kind of redoing this whole sim at a lower frequency, because the dimensions here are heavily dependent upon frequency, and just based on the cost of the components that we would be using for 26 gigahertz, we're looking to tone that down a bit. So to talk more about those components and the circuitry that's going to go into this, I'm going to pass it on to Alex Devonport.
Hey everybody, I'm Alex Devonport, and I'm kind of in charge of the rest of the circuitry outside of the antenna for the wireless transmission project. I'm pretty excited by this recent development that we've had with a fairly directive antenna, because it means that we can actually start to focus on what's going to be driving the antenna and how we're going to be getting power from the receiving end. To that end, I've been looking around to see basically what kind of parts we would want to use for that, which is pretty important, because that decides what frequency we're going to be able to use for our antenna, and therefore how we should design the rest of the antenna outside of a very qualitative sense. So come take a look at this diagram I got for you. As you can see, it's actually pretty simple, since most of the parts that we need will already come as kind of lump packages. I've been doing a little bit of online shopping, and it seems like a good frequency for us to use would be around anywhere from 3 to 4 gigahertz, preferably around 3.5. And I say that because that's kind of the range where we have a lot of parts that we can afford given our budget. It's like, as you can see here, I've got a voltage control oscillator that can go from 3 to 4 gigahertz, and an amplifier that's specifically good at 3.5 gigahertz that we can get for, like less than $40, which is pretty phenomenal for RF components. They're usually very expensive. And so that's what we'll be using to drive the transmitting antenna. That'll give us a signal that we can get up to maybe around 2 volts if we're really clever about it. On the receiving end, it looks a little bit more complicated here, but that's only because you can't buy a really good AC to DC converter, which is what we need to transmit or to convert our microwave signal. It's just in the DC power that you can run something off of. And so this little collection of capacitors and diodes here is called a Greinacher cascade. And it's very similar to basically like a bridge rectifier and a couple of stabilizing capacitors. And so that's just a small set of sundry RF components. That's going to cost, I say less than $20 here. It's probably going to be a lot less than that. But basically the hardware on the receiving end shouldn't be as expensive as it is on the transmitting end. So by the next video update, I'll have a more kind of hard-lined bill of materials that'll tell you exactly what we're going to need.
My name is James, and while we have devised a way to manufacture our paraboloid dish out of ABS plastic and Alex's 3D printer, we still need a way to either coat it with metal or like we described before in our last video, press fit mold it. And what we were looking at is ways to electroplate it with a sacrificial anode here of, we haven't even chosen a suitable material to electroplate it with, but this cathode would then be our plastic dish in that situation. Applying a DC source, we could transfer the metal ions onto the dish in this scheme. Where would this DC source come from? We have plenty of power supplies lying around, so we figured we would use one of these for the process. We were also thinking, since we're using a lower frequency, that we could get away with not necessarily an entire continuous surface, but one that might have holes in it, like this gridded dish here. Or we could use this metal strainer here, or some other mesh, which we could press into a paraboloid dish and use that. We might even electroplate that after the fact. So after we get the parts, the dish, a good schematic going, all that's left is some sort of base to affix everything to it, which we might leave to do for next semester.